In this video for belt scales, we're going to cover principle of operation, installation, programming, and calibration. Belt scales measure the weight of material or material load in an area called the weigh span. The scale processor continuously computes the rate of material by calculating the pounds per foot loading multiplied by the belt speed in feet per minute to equal the rate in tons per hour. Generally, the best place to install a belt scale is about a third up the length of the conveyor and sufficiently far from the end feed to reduce vibration. A good rule of thumb is no closer than 4 to 5 belt widths from the end feed. There are guidelines on curved conveyors, like in this example, 40 feet away from the tangent points of the curve. There will be other guidelines in the manual, but this is an important one to take note of. Be careful about installing a scale close to a training idler, or sometimes you might have a scale working properly, then someone installs a training idler close to the scale. It will cause repeatability issues. Ideally, don't put a training idler within 40 feet of a belt scale. The existing idler is typically removed from the conveyor and modified for the belt scale. It is also a good time to replace any worn rollers or conveyor parts in the area. A support plate or triangle is welded in for strength and rigidity. Then the idler mounts are removed to allow the scale free movement up and down. Sometimes the idler feet are cut at an angle to allow for plenty of space. It really depends upon the idler type you have installed. You just want to be able to have free movement as well as avoid excessive area for material buildup. The idler is centered on the belt scale and marked. Usually this is while the belt scale is sitting on the ground. It's just easier to work with at that time. The unpainted scale mounting brackets are removed and then welded to the idler after marking the appropriate location. You can see here the scale mounted to the brackets and the supports in place. Ideally, you don't want to weld it while it's sitting on the scale or close to the load cells unless you really know what you're doing, because you can destroy the load cells. Idler alignment is the most critical area of belt scale installation. You want to align all of these idlers 3 before and 3 after along with the scale idler so that they're all within 1/32 or better of each other. That way it'll provide a straight path through the scale and weigh properly. Careful placement of the strings is critical to attaining a close tolerance alignment of the scale service idlers. At least 2, ideally 3 before and 3 after, you place carpenter string or fishing line or some good quality string tightly held in place over the rollers, and add shim stock underneath the idlers to bring everything all into the same plane. The belt scale should be installed in the same location where you remove the idler. It's usually easier to do without the idler attached. The scale is mounted and centered so that the idler will be the exact same distance from the idlers on both sides. And what we're doing is checking all of these distances to make sure they're all equal and the same. We may also measure from one idler before to one idler after the scale and divide that by 2 in order to calculate the weigh span. And this is a very important value to have because it will be used in programming the electronics. So here I want to measure one idler before to the scale idler and one idler after. I want to know what those distances are, so that way I can calculate the weigh span. So again, I would measure between there to there and divide that by 2, and ideally I would make those all the same length apart. The idlers that are like 3 before and 3 after the scale we want those to all be the same distance apart as well. So 3 before and 3 after the scale should all be of equal distance. We would place the alignment strings on top of the rollers. Sometimes all we'll be able to do is put them on the outer edge of the roller if we can't lift up the belt. Ideally, the best installations you're able to lift up the belt and also put a string on the center roller down in the bottom part of it and make sure to align everything all up properly. But sometimes that's just not possible. But this is a good example here of showing proper placement of the alignment strings. We want to make sure the strings are well tensioned, and I often will use some bungee cord to secure it down to the conveyor frame and bring those strings in good and tight. I'll also wrap it around like idler number 4 so that way we have a good tension and everything is all kept nice and even and straight. Look at all that distance between the idler and the string. This example is somewhat exaggerated to make it easier to see on video, but what we will do is add shim stock underneath the idler in order to bring it up so that way the roller is in plane and even with the string. These shims provided by Tecweigh are very handy when installing a belt scale. Be sure to have some included on your next order. Now we would add shims underneath the idler mounting brackets and belt scale to bring all of the rollers in the same plane so there are no gaps between the string and the roller. This is really important. Sometimes you might need a crowbar or something to lift that up and then have all the necessary tools there to be able to loosen and tighten. Sometimes you might have to go a little more of like a 30-second larger because as you tighten it down, it will tend to compress those somewhat and take any air gaps. But you can experiment with it a little bit and get an idea on how the best way works for you. But that's it in a nutshell. So now we've completed the alignment on that one side for this one side of the roller, and look, everything is all touching nicely and there's no gaps in between, and it's neither holding up or too high as well. So we don't want to make sure it's too high or too low. We want it right even with this string. Here you can see the shipping bracket. After everything's all done, you can loosen up those bolts and then turn the shipping bracket down to the side so you can always re-engage it later if you're needing to do any conveyor maintenance or replace the belt. A trailing arm speed sensor is commonly provided with Tecweigh belt scales. Make sure the speed sensor is located in an area on the return belt to reduce bounce. Sometimes you may have to use a snubbing pulley to reduce bounce on the return belt as well. A shaft-mounted speed sensor is sometimes supplied based on the application or customer preference. It can be installed on a bend pulley or tail pulley. Just make sure to follow the mounting instructions in the manual. Remember, speed is half the equation, so proper selection and installation is important. Make sure to follow good wiring practices. Don't place belt scale cabling next to high voltage lines. Make sure the cables are protected from material and machinery. Tecweigh electronics typically come already programmed with the scale sizing data supplied at the time of purchase, but it's good to check and verify the key parameters, especially the calibration weight, waistband, which I'm doing here, as well as belt length values, just to double check and make sure everything is exactly what it's supposed to be. You'll have a much better installation if you do that. So now let's take a look at the WP20 electronics. We have a couple of buttons: auto zero, auto span, up and down arrow, the select button, stop count, reset, so forth. If we hit on the select button, it's going to show us the version of software. We hold down the function key, it'll show us the speed, but if we hold it for 5 seconds, it will go into program mode. And in program mode, That allows us to change the parameters as necessary. We can hit function to go forward in the parameters, and to get into a parameter to change it, we'd hit select, and there I'm changing the tons per hour to something different, but I'm going to go back to tons per hour. We're going to use that in this application. I'm going to hit function key to keep moving forward. The cal factor would be pre-programmed in there, plus you can see what the cal factor is you need to use depending on the model belt scale that you have. Calibration weight, that would be the amount, the weight that we have when we add both calibration weights together. It's always good to verify that. We'll program that in at the factory, but you want to verify to make sure that the calibration weight that's on the scale is what's on there. So it's just showing how you can change the numbers in those. We're not using a calibration chain, but if we were, here's where we would enter in the chain values. We can also go backward in the parameter by holding down that key and hitting the function key. Maybe we'll change the waistband value based upon our measurement that we did. We'll keep moving forward. We'll verify the belt length. Maybe what we measured in the field is differently than what was provided in the application data. It's always good to check that. So we want to double check that belt length and move forward through that. We can hit function to keep on going forward. That's where we might do a material test and enter the value in there, the pre and post weight. You can find all this in the manual too. AZT, we're not going to change that for right now, but it's called auto zero tracking. That would allow us to help hold the zero just on the display a little better. Tracking revolutions. Normally we just keep that at 0. 0 revolutions, we could change that to 2 or 3. For most applications, the factory default of 2 is okay. That's the complete revolution of the belt during a calibration. Span revolutions is when we put the test weights on there. That'll tell us how many belt revolutions we want to use for the span calibration. Rate decimal places, generally we leave it 1, but we could change that to something else, and you could see how it affects the rate display. We're going to change it back to 1s and keep moving forward. We'll acknowledge that parameter by hitting select, and we'll keep hitting function to go forward. This would be the rate damping. Sometimes I'll change that just to slow down the movement on the display, maybe up to like 25, for example, which I did in this example. Speed decimal places, that's just like the rate decimal place, meaning we could go in and adjust that. Speed damping, if we wanted to change that, add some damping on the speed value, but generally that's not required. The speed constant, this is going to be pre-programmed for the particular type of speed sensor, but if you measure the belt speed as it actually is, you can go in and adjust that up and down. See, if you hold down the stop count, it'll show you the belt speed, so you could adjust that value up and down till you arrive at the speed you measured, maybe with like a handheld tachometer. That's always a good best practice to do, is double check the speed and make sure speed is being read correctly, because that's half the equation. Remember, speed times the load equal the rate. So that's why it's important to have a good value, a good correct value in there for that parameter. And here we're just adjusting that up and down, but we've finished adjusting that, so we're going to move forward in that area. Move up to milliamp damping. If we want to change that to any particular value, we can. I may increase it up to 25. This is where we could set our 4 milliamp value. Generally, we'd leave the base milliamps at 4. This is for setting up the 4 to 20 milliamp output. And for the most part, here under 20 milliamps, we'd put the max ton per hour. So that way, whenever the integrator or the processor is reporting 500 tons per hour, it's giving out a value of 20 milliamps. Now here's where we can set the low rate trim to adjust the 4 milliamp in order to account for line loss. It's just a very handy tool to have, as well as to be able to adjust for line loss for the 20 milliamp output. Here we can set the total decimal places. Right now it's currently set at 1 or at ones, but if we set it at tens, you'll see that now we have 27.7 tons showing on the display on the totalizer. But normally we'll just leave that at ones for most applications. But it is available to change. Now here we can program one of the relays to function as a total pulsed repeater. That would be a total pulsed repeater. So that way every time the relay opens and closes, we know, for example, that like 1 ton has passed. And here in this parameter, we would set the pulse duration. That's the time for the relay to open and close. In this case, it's set at 1 second. And here we could set how many tons. In this case, it's 50 tons, but normally that's set at 1 ton. So for every 1 ton that passes, the relay will open and close, and you can count those pulses in the PLC. I just set it at 60. There's also a second relay. We could adjust for another totalizer, or we could set it for a rate alarm, for example. There's a lot of different parameters we could program. There's also lock codes. We can lock out the use of it, lock out somebody spanning it and zeroing it, resetting the totalizer. Just make sure to write down the lock code. The ASC is a value that's typically adjusted during material test calibration, or if Tecweigh advises you to adjust it. But it's a value that you can use to account for material test. The span detect is related to calibration, and if it's not at about 750, I recommend changing it up to about 750. It could be 50 or 750. 750 is typically a better parameter to put in there. Now let's look at the load counts. That's the value you see whenever you actually put load on the conveyor. We'll add some calibration weights to the belt scale, and you can see that go up. You can see the load counts rise, and you also see the rate go up too as well. And as we remove those weights, the load count goes down, and so does the rate go down. If we move to the next parameter, we'll see the zero count. That shows our zero calibration baseline. And the next parameter would be the span count. That's our span count baseline, or when we put the test weights on there. And a really good practice to do is after calibration and everything is all done, to go into params and select store now, then go out into the operating mode by holding down function key for 5 seconds and save a backup copy of all the parameters. It's just a really good practice to do. And there you have it. The unit's all programmed and ready to calibrate. Now let's begin with some simple calibrations. I'm going to touch the function key in this case just to make sure the belt's running. We have belt speed. In this case it's 376 feet per minute. Let the belt run empty for 10 minutes. If it's a newly started up belt, if it's been running for a bit, just make sure it's empty and touch auto zero. Hold it down for 5 seconds and the zero will start automatically. And in this case it's going to run for 2 belt revolutions, but we have it programmed to calibrate relatively quickly for the sake of this training video. So as soon as 2 belt revolutions are complete, it will come back and say the calibration's finished and go back into tons per hour. The next calibration we would do typically would be a span calibration. And so then we would apply the test weights or hold it first and then it will say lower cal weights. If you already have the cal weights lowered, then all you need to do is just hit auto span once more to acknowledge that the weights are lowered. So now you can see we have a simulated load value there from our test weights. And as soon as it does 2 complete belt revolutions, the span count will be complete. And there it says raise calibration weight. And as soon as we raise the calibration weight, the calibration is complete. That's a good number to write down, by the way, so that way you can always check it. Even if you don't have time to do a full span calibration, after zeroing it, which is much more important, you can always drop the weights on there to make sure it's showing what you expect it to. I put the weight on there again just to make certain that it's showing what we expect it to. It should come up to around 170-ish in that neighborhood. It's just a good double check to make sure everything's working properly. And here I'm just going to apply the calibration weights so that way you can see what this looks like. I've added one weight, and then I'm going to add the second weight. Make sure you take all appropriate safety precautions in working around conveyors. So I've removed the weights, and then after the calibration is done, I lift the weights just like this. It's truly that simple. People often wonder how often you should calibrate a belt scale. It's a good idea to zero once a week at least. Zero daily is even better. You can put the weights on and do a span calibration once a month, maybe once a week, or even once a quarter. You should really modify that or make your calibration around how often your belt scale is shifting. And remember, the belt scale is not really shifting. The dynamic forces on the conveyor are what's changing. So the idea about good installation and good routine calibration is reducing the effects of those dynamic forces. I would recommend calibrating whenever the scale is no longer reading 0, when it's supposed to be 0, and if you have any doubts about the span calibration, you can always check those and run them on more of a regular basis. With built-in test weights, it makes running a span check very quick and easy. It's always a good idea to do a routine inspection when you do a calibration. Check for material buildup, any binding or stuck material. Make sure the load cells are free of movement, and also check the speed sensor as well. Make sure it's not bouncing or it's jammed up somewhere or getting too much material forming on it. It's always a good idea to do that visual inspection regularly. That'll help avoid problems. Thank you for watching this video. If you would like more information, please check out our website at www.tecweigh.com or give us a call at 1-800-536-4880.